At Rescue Education, we have the best explanation every time. I'm Dr. B, and I'm going to help you easily and rapidly learn organic chemistry. If you like this video, you'll love my self-help books. Learn more about them at rescueedu.com. Let's talk about molecules with two chirality centers. This leads to the possibility of diastereomers and meso compounds. First, we'll study the stereoisomers of acyclic, that is, non-cyclic molecules with two chirality centers. When a molecule has two or more chirality centers, it will have multiple possible stereoisomers. The maximum number of stereoisomers is 2 to the n, where n is the number of chirality centers. So if we have two chirality centers, we get a maximum of 4 stereoisomers. And if we have 3 chirality centers, we can have a maximum of 8 stereoisomers. Often we get fewer than the maximum number of stereoisomers. Let's look at finding all the stereoisomers of 2,3-dibromopentane. It has 2 chirality centers and has 4 stereoisomers. Here's my method for finding all of the stereoisomers in a systematic and organized way. First, draw out the molecule as a flat representation and find all of the chirality centers. Remember, a chirality center is a carbon with 4 different groups. We indicate these with stars. Then we start deriving the stereoisomers. You can pick any of the stereoisomers to draw first. For the first representation, A, I like to have all the groups lined up, and if there are hydrogens, I like to put them back. This arrangement makes it easy to see how all the groups at each carbon are related. It also makes it easier to find RS configurations if you need to. For the second representation, B, I draw the enantiomer of A. This dotted line represents the mirror image relationship between the enantiomers. For the third representation, C, I take A and switch one and only one of the chirality centers. I'm going to switch the second one. Finally, draw the enantiomer of C, which is D. You have now quickly and easily derived all of the 4 unique stereoisomers, and you haven't drawn any duplicates. You could assign the RS configurations of all of the chirality centers. This is not usually necessary, but let's talk about the configurations briefly. If you have drawn the stereoisomers correctly, you should get all 4 permutations. A is 2R3S, and its enantiomer B is 2S3R. C is 2S3S, and its enantiomer D is 2R3R. The rule is that the RS configurations of all chirality centers in a molecule are always reversed in its enantiomer. So you see, we have 2 pairs of enantiomers, A plus B and C plus D. On the next slide, we'll talk about a new relationship between stereoisomers called diastereomers. Diastereomers are stereoisomers that are not enantiomers of each other. There are 4 pairs of diastereomers of 2,3-dibromopentane, AC, AD, BC, and BD. Diastereomers are somewhat different from each other and usually have different physical properties, such as melting point and boiling point. They can have somewhat different chemical properties, like different rates of reaction. Because they have different physical properties, diastereomers can usually be quite easily separated from each other. Recall, enantiomers can't be separated at all using regular methods because they have identical physical properties. If you have a mixture of all 4 of these stereoisomers, you can separate them into 2 fractions. One fraction is the enantiomeric pair A and B, and the other fraction is the enantiomeric pair C and D. The situation with 2,3-dibromobutane is different. Let's look at the flat representation first. We have two chirality centers again, but notice we are already seeing an internal plane of symmetry. This is a hint that you will probably expect fewer than the maximum number of stereoisomers. Let's start again by drawing E, which has all the atoms lined up and the hydrogens back. Then let's draw its mirror image. What you should notice is that the mirror image is identical, and so it's also E. This is a duplicate, and we should cross it out. E is a type of achiral stereoisomer called a meso compound. We'll discuss meso compounds on the next slide. We need to draw the rest of the stereoisomers. We take E and switch only the second chirality center to get F. Then we draw the mirror image of F, which is its enantiomer G. In this case, we have 3 and not 4 stereoisomers. We have E and the pair of enantiomers F and G. There are 2 pairs of diastereomers, E and F, and E and G. Finally, let's note that if you have a mixture of all 3 stereoisomers, it can be separated into 2 fractions. One fraction is the meso compound E, and the other fraction is the pair of enantiomers F plus G. A meso compound has the following characteristics. First, it's achiral despite the presence of 2 or more chirality centers. E has 2 chirality centers. Second, it has an internal plane of symmetry or some other symmetry element. Here is the internal plane of symmetry for E. And third, a meso compound is identical to its mirror image. This second drawing is the mirror image of E, and it's identical to it. That is, they are the same molecule. Pause and try this sample problem. Draw all of the unique stereoisomers of 2,4-dibromopentane. Do not draw duplicates. Identify any meso compounds. Using arrows indicate all pairs of diastereomers. You do not need to assign RS configurations. Let's first draw the flat representation and identify the 2 chirality centers. Notice there is a CH2 in the middle. Also notice that we can already see an internal plane of symmetry, so we should expect less than the 4 maximum number of stereoisomers. Let's draw the first stereoisomer. And again, we'll draw it to line up our groups so it's easy to see their relationships. We'll put the methyls up, the bromos forward, and the hydrogens back. Then we'll draw the mirror image. Notice these drawings take a long time to do because they have a lot of atoms in them. Once you finish drawing the mirror image, notice that both of these molecules are exactly the same. They're superimposable on each other. So what we'll do is we'll just cross out the duplicate so there's no confusion. This means that this compound with 2 chirality centers is a meso compound. Now let's switch the second chirality center so the bromine points back and the hydrogen points forward. And again, what we'll do is we'll draw the mirror image of this molecule. The carbon closest to the mirror, we will put the hydrogen forward, the bromine back, and on the carbon farthest from the mirror, we'll put the bromine forward and the hydrogen back. Now these are non-superimposable mirror images of each other, which means they are truly enantiomers of each other. Then we can identify two pairs of diastereomers, the meso compound and the first enantiomer, and the meso compound and the second enantiomer. Now let's talk about the stereoisomers of cyclic molecules. The molecule 1,2-dimethylcyclopentane exists as 3 stereoisomers, 2 trans enantiomers, and 1 cis meso compound. If you draw the mirror image of the trans molecule, then you see they are not identical. They are enantiomers. If you take this first molecule and try to overlap it on the second, you discover the methyls point in opposite directions. If you try to flip the first molecule, it's still not identical to the second molecule. Build models to convince yourself of this. The cis stereoisomer is a meso compound. You can see its internal plane of symmetry here. Each enantiomer of the trans molecule is a diastereomer with the cis molecule. So we have 2 pairs of diastereomers. Pause and try this sample problem. Draw all of the unique stereoisomers of 1,3-dimethylcyclohexane. Do not draw duplicates. Identify any meso compounds. Using arrows, indicate all pairs of diastereomers. The first thing I'm going to do is draw the trans mirror images. This is a cyclohexane, a 6-membered ring, so I'm going to draw both of my 6-membered rings first. And the mirror plane in the middle. Now it doesn't matter where we draw our methyls. On each one of them I'm going to draw 2 methyls right next to the mirror plane. And then I'm going to draw the trans-methyl 3 carbons away on the left and also on the right. So these are the trans mirror images, and they are in fact enantiomers of each other. They are not identical. So for instance, if you take the left-hand molecule and try to rotate it so you can overlap the methyls, you cannot overlap the methyls. They will always be inverted. And no matter what manipulation you do on the left-hand molecule, you will never be able to overlap it with the right-hand molecule. So these are truly enantiomers. Then next I'm going to draw the cis stereoisomer. I'm just going to take the right-hand trans stereoisomer and flip over the right-hand methyl, and that gives us the cis. And what you should see immediately is that there's an internal mirror plane through the molecule. So this is a meso compound. We don't need to draw the mirror image. If we drew it, it would be exactly identical. Finally, we have to identify pairs of diastereomers. Each enantiomer is a diastereomer with the cis compounds, so we have 2 pairs of diastereomers. Finally, let's look at 1,4-dimethyl cyclohexane. It has only two unique stereoisomers, the cis and the trans molecules. Each of these compounds is achiral. Neither compound has any chirality centers. If you look at this carbon, you see it has a methyl and a hydrogen. Then, as you follow the two sides of the ring, we see that each of them hits the other methyl-substituted carbon at exactly the same time. So these two groups are identical. The same thing happens to all the methyl-substituted carbons in both the cis and trans compounds. We can also see both compounds are meso because they have an internal plane of symmetry. If you look down on each ring, we get a top-side view. We split the two methyls in half, we split the C1 and C4 in half, and each side of the ring reflects into the other. This happens for both the trans and the cis compounds. There are only two stereoisomers, the trans and the cis stereoisomers, and they are diastereomers of each other. If you're using my book, I encourage you to do the extra test your knowledge problems for this topic, so you can be sure you really understand it. All the answers are at the back. This video is closely based on my first semester organic chemistry self-help book. My self-help books are particularly valuable in difficult learning situations, but you can also use them to get an edge or to get a head start. If you want to learn more about my books and videos, how to get the books, or my future projects, go to rescueedu.com.